Hello, welcome to the lecture on response surface methodology under design and analysis of experiments. So, today I will introduce the concept called response surface methodology, which is in abbreviated form we say RSM. Okay. So, RSM is a collection of mathematical and statistical techniques. Mathematical and statistical techniques. This purpose is to optimize the process outcome. Means what I mean to say here that given a process with set of controllable factors, you want to set the controllable factors in such a manner that the response of the process will be the maximum or minimum depending on the characteristics of the response. In general, we can say the optimum response value. So, you want to achieve the optimum response from a process. This is my process, inputs, controllable x, uncontrollable z, process steps, you got output. Now, question is that I want to optimize this output. So, where to set x? What is the zone of x? So that you will get the optimum y. So, what is my desired value? Desired value is the minimum or maximum depending on if y is higher the better or lower the better, or there may be a situation where a target value is important. So, here we are basically talking about the optimum value, that means it is either the maximum or the minimum value. If y is process yield, then definitely you want to set your controllable parameters in such a manner that y will be maximum. If y is that what I can say that defects, process defects. So, then what you want? You want to set x in such a manner that the amount of defect or the severity of defect that will be at the minimum level. Okay. Suppose you are conducting an experiment and you want to see that the impurity level in a particular product will be the minimum. So, that time it is basically minimization case. So, response surface methodology will be useful to find out the optimum process output depending on the nature of the controllable variables, and the relationship between the variables will dictate or will lead to the situation to the level possible. What I mean to say? I mean to say that you want to set x in a particular zone or a particular range, so that y will be having the optimum value. That is the purpose of response surface methodology. So, it is basically a optimization technique. So, what I will do today, I will give you the general introduction to response surface methodology, and then we will show one method called method of steepest ascent, when the purpose is maximization, or method of steepest descent when the purpose is objective is minimization. So, that will be discussed. and with an example the first order response surface model will be discussed. So, let us see what is RSM. I said a collection of mathematical and statistical techniques. This helps in modeling the relationship between y and x, as well as it will help in analyzing the behavior, and finally, it will help us to optimize the response. So, that is what is response surface methodology. So, here I have given you a surface. If you carefully look into this, you see that there are two process variables, temperature, which is denoted by x1, and pressure denoted by x2. So, temperature and pressure that vary from certain range, within certain range. For example, here in this graph 100 to 160, I can say if it is 100, maybe it is 80 to 180, and again that pressure 10 to that 50, at that range it is varying. Now, and according, if temperature and pressure is related to the yield, then what happened, you are getting this surface, the curved surface here, this one is known as response surface. Okay. So, if you take any point on this surface and project towards this temperature axis and pressure axis, then you will get the value of temperature and pressure, and for this yield value can be obtained if you keep the process temperature at that particular value and pressure at that particular value. What do we mean? We have given you here one is this process yield, I think this is yield, and we are saying expected yield, and then what happened, then you see that this axis is your temperature, this axis is your pressure, and ultimately you are getting a diagram like this. Okay. Now, if you take any point here, any point, suppose if I say this is my pressure, this is my temperature, any point here, and from that point when you project there, suppose this projection is here, and then you corresponding position you get there. So, then these are the two values which, for suppose if this is, I can say that 130 degree centigrade, and if it is, this one is my 25 psi, and corresponding this y value is this. So, that means if you run the process at 130 degree centigrade temperature and pressure 25 psi, your expected yield value will be this. Okay. So, this is the way that response surface will be analyzed. Okay. So, this is the way response surface will be interpreted, and that is what is in better manner it is given here. This is my response surface. So, you want to find out that response surface, this is the first thing, and then second one is basically that depending on the nature of the output, you want to maximize the output or minimize the output. If it is a maximization of output, you want to find out the point on this response surface where the output is the maximum, and rather I can say that you have to find out the global maximum, a zone you want to create, that if you operate your process within that zone, then you will have the near optimal that responses. Okay. So, very few interesting things are that what is the response surface. So, all of you have gone through the regression. So, I have given you the regression like this, y equal to x plus beta plus epsilon. Primarily in the regression chapter we have discussed the first order model. That means I can say that y equal to beta 0 plus beta 1 x 1 plus beta 2 x 2 plus beta k x k plus epsilon, and this portion is coming under x beta and epsilon is there. So, in general this that means this can be y can be written as f x 1 x 2 like x k and plus epsilon. With reference to this example, our y is f of x 1 x 2 plus epsilon. Okay. So, then the response surface is this response surface eta is basically the expected yield for different values of x, which is function of x 1 and x 2. So far whatever design we have employed, experimental designs, and the results what we got, finally everywhere I have shown you the regression equation. That regression equation basically talks about the response surface. By first order regression equation or first order model, we say that basically the interaction and the higher order effects are negligible, only the main effects are of importance. So, in regression the main effects we have considered, but if you see the nature of this response surface, it may not be a main effect model only. There may be interactions or higher order effects, some kind of maybe second order effects are there. So, by saying eta equal to f x 1 x 2, so this may be a function of the main effects, interaction effects, and higher order quadratic, maybe the quadratic effects. So, you want to find out first this, whether the first order model or second order model or higher order polynomial are required, that you will be finding out. And once you have that response surface, you also want to find out where the optimum response lies. So, that is the purpose of response surface methodology. Okay. Now, what I will show you these two response surfaces here. One is your first order response and another one is second order response. So, first order response and second order response, how it looks like. If there is no interactions and higher order effects, so then the response line will be this flat type, this one. Okay. So, and if there is second order effect interactions, then the regression line surface will be that kind of this curve will be there, curvilinear surface. And in the first case, if you suppose you want to develop contours, I also explained contours earlier. I said that suppose this is your temperature and this one is pressure. So, then y contour, the response contours. That means for certain values of temperature and pressures, what happen, the y response will be same. For example, if that means if temperature is this value, pressure is at that value, then response is y. Suppose this is y 1. So, any point on this line is having same value for response, but if I take a point here, the temperature and pressure, that value will change like this. This is the process temperature, this is the process pressure. If I take this point, the temperature is reduced, pressure increased, but in both the operating values in terms of pressure and temperature give you the same value of y. So, this is the contour. So, maybe the second contour, third like this. Okay. So, this is y 2, y 3, y 4, y 5, something like this. Okay. So, if you do not have the interaction and the higher effects, then your response contours will be like this, the parallel lines. Means if the first order model is fit here, then if you develop the contour for the response, you will be having parallel lines. If your second order model is fit, then you see the contour. What is happening? This is the first contour, y is 70, this is the second contour, y is 60, this is the third contour, y is 50, fourth contour, y is 40, like this. The reason is the maximum value is like somewhere here. So the second case, as per the contour is like this, maximum value here, and your contours are reducing like this. So it's some kind of hill. Here the maximum height, then this height, then this height, then this height, then finally this height. So you are getting this one with reference to this. So this is nothing but you just go periphery of the hill. It may be it is basically your case may be just reverse. It can be other way around also, like this. So in that case, the response surface will not be like this. It will be like this. What I mean to say, it will be like this. When the between point, it will be down like this. So it is. Now if your maximization case, suppose this is some kind of hill, and it will minimization case, say this is some kind of valley. So your response surface will give you, depending on the number of variables, obviously that the surface will be different, but for the explanation point of view, if we consider the two controllable factors or variables, and then if it is a maximization case and where the higher order interactions are there, including the higher order effects, quadratic and higher order effects. So you will be having a hill kind of structure or valley kind of structure, depending on whether it is a maximization case or a minimization issue. Interactions or the effects are not there, then what happen? It is a surface plane. It is a surface. Maybe the surface will be plane surface, some inclination will be there. Okay, it is not that constant, that is slope. For example, here this surface. Okay. So response surface methodology will help you in finding this surface, and also helps you in identifying the optimum zone of operations. Okay. So now let us discuss that what is the approach adopted by in response surface. So for this you require to have some more concepts. What are those concepts? So let us write down. Change. Okay. So suppose you just think of, for the time being you think of the same, that pressure and temperature. Pressure may be x2, temperature is x1. Okay. So these are the basically controllable factors. This will give you the design space, where you will operate. Suppose you just think of, so this is the overall operating zone you can operate, means temperature from here to here, pressure from here to here. For that, and you want to find out that should you work here, operate the process here, should operate the process here. Suppose you are operating somewhere, but without doing this kind of experiment, based on process knowledge and maybe previous experience, you started with doing somewhere. So there may be some technology changes and other things have happened, or you may be thinking that no, this zone, this operating zone is inferior, this operating zone is superior, or this will give you the optimum response, not this one. So, how do you know? So, for that purpose, that you must know what is your current operating conditions. For example, suppose you are doing here. Then using response surface methodology, what you want to find out first? You want to find out the direction of improvement. If we assume that this is basically the region of optimum, then response surface will give you these directions. It will give you these directions. Okay. So, first your approach is that you know your current operating conditions, then do experiment here, fit a model, response surface model, and then from there analyzing that model you find out the direction of improvement. So, this is our direction of improvement. Okay. So, that means your one set of experiment is not sufficient, one experiment is not sufficient, one kind, you have to have several experiments. So, set of experimentation, this is basically I can say you have to do sequential experimentation. You do here, find out the direction, go to the second place, again feed the response surface and see that whether optimum point is reached or not. If not, again you find out the direction from there, and in that manner you finally reach to the region of optimum. That is why response surface is sequential in nature. So, you see that this is your current operating conditions. Now, what is there? So, you have you know that in the operating that zone. So, if you operate here somewhere here, the process output value, response value will be somewhere, let it be maybe 67, and now if you go along this line, suppose assume that you know, then this 70, 75, these are all the contours. So, that means this is the direction of improvement, but actually you do not know that, and so what you want this direction, and response surface what it will do, it will first when you conduct experiment here and then fit a regression model, that regression model will help you to go either this direction or this direction or this direction, means maybe this direction, maybe some this direction or this direction or this direction, depending on the model will guide you which direction you will go. And the purpose is basically you want to reach the vicinity of the optimum. So, that is why finds out the path of improvement towards the optimum. Now, if it is a maximization case, as I told you, you are climbing a hill. If it is a minimization case, you are descending along the or into the valley, that is the case. So, this is what I have given you. Okay. So, now there are few more issues here. That issue is that when you are considering such a bigger zone, and at some zone you are working, and if it is not the point of optimum, what will happen, that you will find out that the lower order model will become sufficient to find out the direction of optimum. You do not require to go for higher order model, because this is the place where your optimum value is not reached. This is the operating conditions where you are working suboptimally. So, under thus that condition, because you want to go, it is not a localized one, you have a broader perspective. So, you will see that at the aggregate level what happened, the lower order model will work. So, and if this is not the point of optimum, here you may fit a first order regression model, and then from that model find out the point of optimum, direction of optimum, and then follow that direction, do the next experiment, again fit the model, first order model. If first order model does not fit there, that means you have to go for second order model. That means there is a curvature or quadratic effect, a point of optimum might have reached. Okay. So, if it is a maximization problem, we will say that the method is, the optimization method is basically steepest ascent method. If it is a minimization one, it is will be steepest distance method. Okay. So, whatever may be the case, but let us explain only the steepest ascent method, because the descent will be just the reverse. Okay. So, let us see that suppose the first order regression model is fit, then your predicted value will be beta 0 cap plus beta I x I sum of this. Now, if you plot the contours for x 1 and x 2, as it is a first order model, and that means there is no interaction effect. So, you are getting a surface, and where there will be parallel lines which basically gives you the contour for response. So, here you see that y bar y cap equal to 10, y cap 20, y cap 30 like this. So, these are the contours. So, you are at present you are operating here. So, now from the contour plot you know that where you should go in this direction, but what is that direction? So, first where you are operating, you have the origin. So, you take from origin a perpendicular distance towards this contour, these are all perpendicular to this, you are getting a surface. So, perpendicular to that surface from the origin you move. Okay. So, normal to the fitted surface, perpendicularly normal. So, that means what is the path of steepest ascent? The line through the center of the region of interest and normal to the fitted surface. So, here you basically started working, here is the center and you have the surface. So, from here you take the normal path, normal to this surface. So, you will be getting, this is the direction. Okay. Now, what happened? The steps along the path are proportional to regression coefficient, very important. So, you have beta 0, beta 1, beta 2, beta 3 like this. So, beta I and beta j. So, beta I basically how do you get this path using the regression coefficient? The concept is that the path are proportional to regression coefficients, number 1. The actual step size is determined by the experimenter based on process knowledge or other practical considerations. Experiments are conducted along the path of steepest ascent until no further increase in response are observed. So, what I mean to say, y cap is beta 0 cap plus sum of beta I cap and x I equal to 1 to k. This is our first order model. So, with reference to this temperature and pressure case, we can write beta equal to beta 0 cap plus beta 1 cap x 1, beta 2 cap x 2. So, beta 1 is the regression coefficient for temperature, let it be, and beta 2 regression coefficient for pressure. Now, this beta 1, beta 2 will tell you which direction you will move. Okay. Because that will be basically the steps what you take, you should not take along x 1 or along x 2 only. Your beta 1 and beta 2, the coefficient will guide you whether you will, how much you will go along x 1 and how far you will go along x 2. So, that we will be discussing definitely. Now concept is that how far you will go. If I say so you, this is the zone, you have started with this and you are moving to this direction. So that means what happened, you are first you are experimenting here, then suppose you want to experiment here again. So that means how much you are moving from here, you are here from x1 point of view, x2 point of view, we are here originally, you want to go this. So this much movement, and here it is this, and you want to go this much movement. So that means these are known as step size. So step size for x1 you may choose, or x2 you may choose, that okay, at this point suppose if it is x2, then this one is x2 plus delta x2, and if this is x1, maybe x1 plus delta x1. If you choose delta x1, then delta x2 will be automatically determined, because we have beta 1 coefficient here and beta 2 coefficient here with reference to the first order model. Now then which variable you will choose? You will choose this is the step size for that variable where you have maximum knowledge, or which is having the maximum contribution in terms of beta. So that means you start with the variable to find out the go to the next step for experimentation. You start with the variable which is having either the maximum beta coefficient, or you have maximum amount of knowledge for that variable, and then the other one will be determined accordingly, because you know y cap equal to beta 0 plus beta 1 x1 plus beta 2 x2, this is known. Once you choose this delta x1, and where the increase is beta 1 per unit, then what will be the change in x2. So that considering beta 1 cap and beta 2 cap, you will be finding out the x2 value. So that is what we are, and I will tell you that the computation issue, but the issue is that the actual step size means in order to go along this line, you require to choose steps. That means how far you will go. You may say I will do here, it may not work. It may be the distance is so high that in between there are points which are basically it is gives you maybe who knows that the maximum lies here, not lies here. So this direction you got, and you follow that direction, and finally conduct experiment everywhere, here everywhere, and finally you will find out a position where the maximum value will reach, and when you go beyond that the optimum value will decrease. That is the concept I will is used here in the method of steepest ascent. Experiments are conducted along the path of steepest and no further increase in response is observed. What does it mean? Same thing, suppose your current operating zone is this, and you got the regression line, that what I can say, that this one regression surface, and you know the from the contour you know this is the direction is known. So here you conducted experiment, you got the y value, response value. Suppose if I say this is response. So and then this is my first experiment and my response value is this. So this direction, suppose you are doing here the second set of experiment, your response value is this. Third set of experiment here, response value is this. Fourth response value is this. Fifth response value is this. Sixth response value is this. Seventh response value is this. Eighth response value is this. So what does it mean? You are going along the direction you are going, and finally your curve is like this. So this is the, suppose if it is the kf that is mth step, this is the maximum one. Below this you have less value, and above this also you have less value, and here you got a curvature. We will then start with an example. but I will complete the example in the next lecture. In this lecture, just I will explain that what is the example and what the results we got, but the details of the results, all those things will be explained later. A chemical engineer is interested in determining the operating condition that maximizes the yield of the process. Two controllable variables influence the process yield: reaction time and temperature. The engineer is currently operating the process with a reaction time of 35 minutes and temperature 155 degree Fahrenheit, which result yield around 40%. Because it is unlikely that this region contains the optimum, she fits the first order model and applies the method of steepest ascent. Okay. So, that means suppose you are again reaction time and temperature, reaction time and temperature, and you are operating here, current operating 35 minutes and 155 degree Fahrenheit. This is the center point. So, that means I can say this 30 to 40, maybe this one is 150 to 160, something like this. This is the range you are working with. So, you conduct an experiment and get the values, and that experimental result is given here. Here what happened? Here a factorial experiment with center point is used and experiment is conducted. Fine. With this data, what happened? The coding, and there are three kinds of things to be estimated. One is the error estimate. So, error was estimated using the central data. Then your interaction estimation, that is also estimated with the factorial data points, and then through F test we say that interaction effect is negligible. And then quadratic effects is estimated, that how to estimate the quadratic effect. One lecture we have already given you using the central point how quadratic effect will be estimated. So, that was estimated, and using F test found out that quadratic effect is not there. So, interaction is not there, quadratic effect is not there. Then what happened? The beta coefficients, their significance was tested also using the standard deviation of the beta coefficient, and it was found that the standard deviation value is very low compared to the magnitude of the beta values, like our beta values are 0.775 and 0.325, and standard error is 0.10. So, they are quite large with reference to the standard deviation. So, we can say that first order model is significant. That means, this model will help us in finding out the direction of optimum. So, using this, then as I told you that you first in the origin set the origin, and then you find out the step size, and then you go on changing the values of the two variables and conduct experiment one after another and get the response values. Once all those response values if you plot, you will be getting something like this. So, obviously, based on the first order model and the subsequential experiment, you have reached to a point where step size, I think this is 10th, this 10th step size. Here you are finding out that what is the x1 and x2 value, and that is giving you that what is the value of y. It is y value is all more than 80%. So, if you see this, suppose I say the 10th one means your that natural variable, the temperature and reaction time and temperature is 85 minutes and 175 degree centigrade, 5 degree Fahrenheit. Your the response value is 80.3. This is the maximum value you reached. So, that means earlier you were operating I think you are operating 35 and 155. So, but that is the inferior zone. Your better zone is definitely 85 and 175, because the yield is increased from 40% to 80%. Okay. So, 80%. So, now what you require to do, at this zone you conduct another experiment keeping the center at 85 and 175 and again fit a first order response surface, and you see that whether the first order response surface is sufficient or not. If sufficient, that is not the optimum point. Then you have to go for again using that response regression values, response surface, find out the direction again and follow that direction, so long you are not getting a zone where curvature effect is there. For example, the once we have fit the first order effect in that new zone, what happened, we found out that pure quantity effect is significant. So, it is in first order will not fit, you have to go for higher order model. Okay. So, this is what basically the way a response surface will work. So, in the next half an hour, what I will do, I will elaborately explain the example. The concept is given to you now. Now, next lecture we will explain those concepts with reference to the example, and we will show you all the calculations and the results, corresponding results and their interpretation, and then what we should do next. Okay. So, to conclude, I say the response surface methodology is a very powerful technique and heavily used in analyzing the experimental data, particularly to find out the zone of optimum, or we want to go to the vicinity of the optimum. And at the same time, what happened, once you know the zone of optimum, you will set your process parameters accordingly and you get the best results what is achievable from that process. You should not run a process at the inferior level. You should achieve the optimum one, the best possible outcome or outputs from such a model. It is a wonderful technique. Thank you very much.